Okay, in this video, we're going to talk about how we measure energy in things. In the previous videos, we've talked about energy and energy transformation. Let's see how experimentally you actually measure this stuff. That is, let's say you enjoy some delicious nacho cheese Doritos. How do we know there's 150 calories per serving? Well, we use what's called calorimetry for that. So just some basics. Delta E equals Q plus W. We know that. So if we know heat and work, we know delta E. We've covered that. So if you do calorimetry, you usually don't want to worry about work. So if we're in a situation where work is zero, and so if we're talking about pressure volume work, if we don't change our volume, we're not doing any work, then W is zero, so the change in energy of our system is just heat of the system. And when you're doing chemistry, you can't really track the change of individual chemicals, but we can measure surroundings. For example, if you have an experiment in water, you can measure the change of water, that's your surroundings, and that if that change in heat is only due to your system, you know the heat in your system. That's basically what calorimetry is. Don't do any work, measure heat change in your surroundings. And so this is a calorimeter. Calorimetry is basically just measuring thermal energy exchange. And a bomb calorimeter is what's pictured here. We have a sample, and you have oxygen, and you have some ignition wire surrounding water. You blow up your substance. You measure the change in temperature of water. We know the heat capacity of water. We know the weight of water in our calorimeter. Therefore, we know how much energy that our water absorbed. And since we're in a sealed environment, that energy was from blowing up our system. So we know that heat came from our system, so that heat was in our system. That's how we know Doritos have 150 calories. We use bomb calorimetry. We also have to take into consideration the heat capacity of the calorimeter, because it's not only the water being heated up, but it's our system as well. So the heat of our calorimeter equals our calorimeter constant times delta T. And the heat of our calorimeter equals the minus heat of our reaction. Okay, so I have looks like complicated problem, not too bad. 0.514 grams of biphenyl, and we blow it up in a bomb calorimeter. The temperature in our surroundings rises 25.8 degrees centigrade to 29.4. So for this, find delta E reaction of the combustion of our biphenyl in kilojoules per mole of biphenyl. The heat capacity of the bomb calorimeter, in a separate experiment, we determined that is 5.86 kilojoules per degree centigrade. So look at the equations from the previous slide, see if you can work this out. Come back when you have an answer. Okay, so the heat of our calorimeter, Qcal, equals the heat capacity of our calorimeter times the change in temperature. And we know Qcal equals minus Q reaction. And the energy of our system is Q reaction. Those are the three equations we need to solve this problem. Qcal is just the heat capacity multiplied by change in temperature, final minus initial, and that's 21.1 kilojoules. If we know Qcal, we know Q reaction, so it's minus 21.1 kilojoules. However, I want my answer to be in kilojoules per mole, so I need to know how many moles of biphenyl we have. We have 0.514 grams of biphenyl. We look at the molar mass, we calculate the molar mass, it's 154.21 grams per 1 mole. So we have 3.33 times 10 to the minus 3 moles of biphenyl. So if we do that, we take this 3.33 times 10 to the minus 3 and divide by 21.1, and we should get this minus 6.37 times 10 to the 3. This should be divided by moles, kilojoules per mole, so I apologize for that, but that is how we do this problem. Just break it down step by step, And don't get overwhelmed, and you should be able to solve this no problem. And that's it for bomb calorimetry. See you in the next problem or next video.